Hi, PyCon 2021. Welcome to my talk, Patterns of Machine Learning Models in Production. My name is Simon Mo, and let's get into it. So what is this talk about? By talking about machine learning models in production, I mean the steps that typically happen after you train a model. Well, a typical answer is to put it in production. But what does that even mean? As we'll soon see, there isn't a very simple answer. One does not simply put ML models in production. There are so many tools for training the models and serving just one model. You may recognize a few of these tools on the collection of logo on the left. These tools help you run and deploy one model very well, but when you actually want to do that in real life and put it in production, it's not that simple. Sometimes scaling beyond one copy of the model just isn't supported. Sometimes you as a data scientist or ML engineer have to work through complex YAML configuration file and learn custom toolings and become Kubernetes experts. And sometimes you hit the scalability or performance issue very early on. Even if all these worked well, many of the tools are very costly and often lead to underutilizing the resource. We need to recognize the reality that there's always going to be new machine learning model trained and deployed over time, and there's always going to be a need for production use cases to scale beyond one copy of the single model. And additionally, for many complex real-world use cases, you need to compose multiple models together. So that's what this talk is about. How does many models run in production, and what are some of the patterns used today for that? Well, who am I? Currently, I'm building a Python library called Reserve at Anyscale, and previously I worked on prediction serving system at UC Berkeley Rice Lab. In both places, I'm constantly talking to machine learning practitioners to learn and improve the tooling around ML in production. If you're tuning in, you're probably an ML engineer or data scientist or even just enthusiast. You're excited about deployment and ML in production, and hopefully you can take away some useful tips and tricks from the talk today. This talk will be broken down into two parts. First, we're going to cover some patterns that summarize from 100 or more user interviews conducted by me and the teams at Anyscale. And then I'll talk about Reserve, a framework we built from the lesson learned. It has a simple-to-use Pythonic API, and it is especially built for ML models in production. We'll start from the very high level. Architecturally, where do you put ML models in production? There are three categories: batch, stream, and serve. These are in their order of latency guarantee. Batch workload on the one end of the spectrum has high latency, but also perform inference on high throughput. On the other end is serving, where the use case for low latency is optimized. Let's quickly go through them one by one. In the batch mode, the model is ran in regular cadence by either a scheduler or workflow manager. It's kicked off to score new batches of data and use newer models to score old batch of data. The operation is essentially replicating the training and scoring phase of the training pipeline. In the streaming mode, incoming events are coming in constantly into the stream processing engine like Kafka, Flink, or Spark Streaming. They'll compute features in real time and run small batches through the ML model. And then lastly, there is the serving architecture, where the models are served in real time for interactive use cases. We'll focus on serving because it is not only the superset of batch and stream. After all, if you can serve in low latency, high throughput, you are well positioned to run it in stream and batch scenario. But also, serving covers quite a majority of use cases that we have observed. So that's a high-level architectural pattern. Now let's take a look at 4 concrete patterns we'll cover today. There are pipeline, ensemble, business logic, and online learning. These are core pieces of common machine learning app in production today, and we'll take a close look at each one of them, showing their pros and cons and use cases. So let's start with pipeline. Let's take a look at a typical pipeline. Showing here is a computer vision pipeline where we will use multiple deep learning models to capture the object in the picture. Starting with a raw image, it will need to go through some pre-processing like image decoding, augmentation, and clipping. And then it's passed into deep learning detector or classifier. In here, the model identifies the bounding box and the category. Well, it's a cat. Once we detected some object, the image is passed into a key point detection model to identify the posture of the object. So the model identifies key points like head, neck, and the head. Lastly, we run through featurization with all these inputs and generate a category of what this picture shows. Well, in this case, a standing cat. While this example might seem a bit contrived, a typical pipeline rarely consists of just one single model. To tackle real-life issue, a machine learning application uses many different models to perform even a very simple task. Pipeline in general breaks a specific task into many steps. Each step is conquered by a machine learning algorithm or some procedure. You might be familiar with scikit-learn pipeline construct, where you can combine multiple models or processing objects together and call the fit function as a whole. There's also common pipeline setup in recommendation system, where a typical recommendation like item recommendation in Amazon or a movie recommendation on Netflix goes through multiple stages like embedding lookup, feature interaction, nearest neighbor model, and ranking model. Additionally, there are very common use cases where some mega machine learning model takes care of the common processing for example, text or images. And these mega model can be the state-of-the-art featureizer trained using millions of dollars worth of compute time, for example, GPT-3 or even giant image models. And then different teams or pipeline will utilize the same model to downstream tasks with lighter and cheaper models like decision tree or some sort of boosting model for specific business-specific task. Thinking about the pros and cons of the pipeline pattern that is very common and widely used, it encourages separation of concerns and each model can be updated separately. In this pattern, each models tackle one part of the task and there are modular components. However, as a downside, the dependency of the downstream models on the upstream models make it tricky to reason about what and when to retrain. If the upstream model was retrained on the new data, then the output feature space of the upstream model will change. The old downstream models will no longer be accurate. In this case, you have to retrain the downstream model as well. However, the reverse is not the case. You can continuously improve the downstream model like decision tree without retraining the upstream mega featureizer. Additionally, they're tricky to parallelize and scale. What do I mean by that? One constant thing of today's talk will be thinking about how can these be implemented. In general, there are two approaches. You can either wrap your model and orchestration in a web server. For example, in the left code block here, models are loaded and ran in a for loop during the web handling pass. Whenever requests come in, we load the model, well, they can be cached, of course, and run through the pipeline. This is simple and easy to implement. However, a major flaw is that this is hard to scale and is not going to be performant because each request were handled sequentially. On the other hand, you can use specialized microservices, essentially build and deploy one microservice per model replica. These microservices can be native machine learning platform, Kubeflow, or even hosted services like AWS SageMaker. However, as the number of models grow, the complexity will drastically increase. The operation cost will also skyrocket. Before Reserve, which is a framework we'll talk about later, you have to choose either the left or the right solution. Now let's switch gear a little bit. In many cases, pipeline is a good pattern to have. However, one limitation is that oftentimes there can be many upstream models for a given downstream model. This is where ensemble patterns come in. One is for model updates. As we mentioned before, new models are developed and trained over time. This means there will always be new versions of the model in production. How do we make sure that the new models are valid and performant in the live online traffic scenario? We can put some portion of the traffic through it. This is one possible use case of model ensembling, where you select the output from a known good model while it runs through and collect live output from newer version of the model. And then the second use case I'll talk about here is aggregation. This is one of the most common definition ensembling. If it's a regression model, the output from the model are typically averaged. And for classification model, the output are typically a voted version of the output from the upstream models. For example, two models says the image contains a cat, and one model says the image contains a dog. Then the output would just be a cat. Aggregation helps to combat inaccuracy in each individual model and generally makes the output more accurate and safer. One more use case for Ensemble is to dynamically perform model selection given input attributes. For example, if the input contains a cat, then it will use model A, maybe trained specialized for cat. If the model contains a dog, then we'll use model B, specialized for dog. Note that this dynamic selection doesn't necessarily mean the pipeline itself has to be static and choose given an attribute. You could also be selecting models given user feedback. Implementation-wise, we still have the same sort of issue. On the one hand, you can wrap the models in the same web handler and run the models through the critical path of web handling. On the other hand, you end up having a lot of microservices to manage. The number of microservices scale by the number of models, and we have the same issue as pipeline. Choosing web server means simple but not performant. Choosing specialized services means complexity and operational overhead. So that's pipeline and Ensemble. Let's take a look at two other common patterns we observed. One of them is business logic. By business logic, we mean everything that's involved in a common machine learning app that are not the machine learning model inference itself. There are common operations like database lookup for relational record, feature store lookup for pre-computed feature vectors, web API call for external services, or even just inline feature transformation like data validation, encoding, and decoding. Productionizing machine learning will always involve business logic. No models can be a standalone and serve requests by themselves. As the meme says, business logic is everywhere. However, there is one critical issue around the business logic in ML-based application. Well, let's take a look at the pseudocode on the left here for the web handler. We first load the model, say from S3, and then validate the input using a database, and then look up some pre-computed feature from an external feature store. Once we have completed all this business logic, the input will be passed through the ML model. Can you spot the issue here? While the model loading step, database lookup step, and feature store lookup step are network bounded IO heavy, the model inference step is compute bounded and memory hungry. This requirement for model inference and business logic lead to the server being both network bounded and compute bounded. This is bad because we cannot efficiently utilize all the resource, and scaling the kind of app will be very expensive. One common alternative is to split the model out into a model server or microservice. This approach shown on the right is often a solution to increase utilization as compared to a web server deployment model on the left. With the splitting, the web app is now purely network bounded. While the model servers are compute bounded, each server can scale separately. However, a common problem is about the interface between the two. If we put too much business logic into the model server, then the model server again will become a mix of network-bounded and compute-bounded calls. But if we don't do that, let the model server be pure ML model servers. Then you have the tensor in, tensor out problem. This term I defined to describe this kind of interface problem. The input type for model server is then typically very constrained to just numeric tensor or some alternative form. This will make it hard to keep pre-processing, post-processing, and business logic in sync with the model itself because they are located in two different services. And because that, it becomes hard to reason about the interaction between the processing logic and the model itself. Because during the training, the processing logic and models are very tightly coupled. But in serving time, they are now split across two servers and two implementation. Again, we'll see the current industry either have to choose left or right, but none of them are satisfactory. So that's the business logic in production ML app. I'll now present a final pattern here about online learning, which is an emerging pattern that becomes more and more widely used. By saying online learning, I mean that the model running in production is constantly being updated, trained, validated, and deployed. There are different paradigms here. I would say online learning is by far the most cutting-edge modes of deploying machine learning model in production today. There are use cases for dynamically learning model weights online as users interact with your services. These updated model weights can contribute to a personalized model for each user or group. There are also use cases for learning parameters to orchestrate or compose the model. For example, learning which model does the user prefer. This manifests often in model selection scenario. As users interact with the application, the preference toward which model will be updated, and a lot of times through the contextual bandit algorithm. And lastly, there is paradigm for reinforcement learning. RL is a branch of machine learning that trains agents to interact with the environment. Let the environment be, say, physical world, simulate a physical world, or even artificial environment for business scenario. One popular example of RL is AlphaGo, an agent that beat human in Go. RL is getting more and more popular for recommendation system as well, because it can train the agent to interact with live environments in an end-to-end fashion. Online learning is very much an emerging trend. It is very powerful, but we still don't have the standard practice on how to get it right. Here I list a few potential questions. When do we know the model is performing well? When is it safe to update the model? And can we ensure personalized models can never go wrong and deliver biased predictions? So that's all the pattern we're covering. There are pipeline, ensemble, business logic, and online learning. As we mentioned before, we discovered the gap in the current implementation for these patterns. So we built Reserve, a framework that encodes and enables these patterns. Let me tell you more about it. Between wrapping the model in the same web server and splitting everything up into specialized microservices, Reserve offers the best of both worlds. It has the simplicity of the web server, but it gives extra power to scale out and parallelize individual components. It is especially built for multiple model in production scenario. How does it do that? Well, Reserve is built on top of Ray. Ray is a framework that provides a simple universal API for building distributed application. And Reserve is simply a framework on top of Ray that's specially built for deploy and scale ML services. Let's dive a little bit deeper into Ray, and this should help understand what makes Reserve a natural fit for deploying models in production and implementing the patterns we laid out before. Ray at its core is an open source library for parallel distributed Python. It takes arbitrary Python function or classes and translate them into distributed setting. For example, here we have many functions on the left and invocation of this function, and on the right, we have stateful classes. To run the application on Ray, all you need to do is just decorate the function with ray.remote. And then it will turn the function into Ray task and the class into Ray actor. With a remote task on the left, you can invoke the task and the task will be ran in your remote worker without you changing anything. The input argument is still the Python object, but the output becomes a reference to the eventual output of the task, which is something you can retrieve later using ray.get. With remote actor on the right, you can specify arbitrary resource like num GPUs to aid Ray scheduler to spawn the process containing this class into a machine with one GPU on them. Now you can call the actor just like normal Python class in your process. The only difference is that class will be hosted on a remote process. And then again, while Ray provides the primitive for distributed applications, Reserve is an API and framework purposely built on top of it. Reserve has three simple concepts that brings the best of both worlds. They are deployment, ingress, and handle. Let's first talk about deployment. At the core of Reserve is a concept called deployment. It is a single unit of code that can be deployed into a remote Ray actor. It has some HTTP prefix, so HTTP proxy can route traffic to it. To declare a deployment, you just need to annotate your class with the decorator. Note that regular init and other methods just works. Once you call my_deploy, Serve deploys your code to the Ray cluster, and the classes is now queryable from HTTP. Let's take a closer look at the architecture diagram on the right. Reserve can scale from your laptop to many, many machines. Here, we just generate them as Ray nodes. Reserve has a controller actor that performs ghost-driven control loops that tries to reconcile the desired state and current state. It is responsible for managing, creating, and updating replica actors. Reserve also provides a high-performance HTTP proxy that's built on top of the fastest Python async server UV-Corn. When a web request comes in, Reserve proxies the HTTP request and route traffic to the deployment actor. So what happens if we want to scale out? The deployment can easily scale to many replicas across many machines. All you need to do is to change the argument in the decorator. When non-replica is specified, reserve starts 10 copies of replicas. Each machine uses one GPU. Each replica uses one GPU. And the HTTP proxy will automatically load balance across replicas. Of course, scaling up and down can also be performed at runtime without any application downtime. So that's the Reserve deployment. But what about more complex web feature? Reserve natively integrate with Fast API, which is a type-safe and ergonomic web framework. Fast API has features including automatic dependency injection, type checking, and validation, Open API doc generation as well. You can directly pass a Fast API app object into a Reserve with serve.ingress decorator. We can make sure that all existing Fast API routes would just work, and you can attach new routes with a deployment class, so states like loaded model, network database connection can easily be managed. Architecturally, we just make sure that your Fast API app is correctly embedded into the replica actor and scale out across many read nodes. Finally, in Reserve, you can directly call other deployments within your deployment, and this can be a nested arbitrary div. What does this mean? Let's take a look at the code snippet that implements a simple two-stage pipeline. In this file, in the file, we have three deployments: featureizer, predictor are just regular deployments, and then the orchestrator receives input, pass it to the featureizer via the featureizer handle, and then pass the feature to the predictor. The interface is just Python. You don't need to learn a new framework and learn a new DSL. As one of my colleagues would call it, you can just write your for loop however you want. Serve handle gives you the flexibility similar to embedding everything in the web server, but without the downside. Serve handle allow you to directly call other deployment that lives in other processes on the other nodes. This allows you to scale out each deployment individually, and the handle calls will be low balance between the replicas. With Reserve, you can arbitrarily compose your deployment together to implement all four patterns. We have shown in the pipeline code sample, Ensemble should be straightforward and similar. We'll now give you an example of business logic in Reserve. Here are the simple change to the old web server code that implements business logic. Instead of loading the model directly, we can retrieve a serve handle that wraps the model and offload the computation to another deployment. All the data types are preserved, and there is no need to write tensor in, tensor out API calls. You can just pass regular Python types, and additionally, the model deployment class can stay even in the same file and deploy together with a prediction handler. This makes it easy to reason about the code end to end. Model.remote looks like just a function, and you can easily trace it to model deployment class. In this way, Reserve helps you split up business logic and inference into two separate components, one I/O heavy and the other compute heavy. You can now scale each piece individually without losing the ease of deployment and ability to reason about the code end to end. Additionally, because model.remote is just regular function call, it's a lot more testable than separate external services. So that's the power of Reserve, a framework we built for scaling out ML models in production. It has three core concepts and APIs. Deployment helps you to create a scalable deployment and update them over time. Ingress helps you integrate with fully featured HTTP application. Handle enables arbitrary nesting and composition of the deployment. With these three concepts, Reserve gives you the best of both worlds between wrapping your model in web server and manage many different microservices. In conclusion, machine learning models in production means many models in production. Over the lifetime, models are retrained, updated, and redeployed. Models are added and scaled out. We covered in this talk, we covered 4 different patterns and show that existing tooling doesn't work well with the multiple model reality. Reserve is built for such reality, and it is the best of both worlds between wrapping the model in web server and working with many different microservices. To learn more about Ray and Reserve, check out ray.io and reserve.org. We're also holding the second Ray Summit in late June. It's free and you can check out more production use cases of Ray and Ray Serve. And lastly, the company behind Ray and Ray Serve, Anyscale, is hiring. Check it out. Thank you.